My name is Richard, and today I'm going to be talking about my fourth year thesis project, which is called Optimization of Closed-Loop Neuromodulation Systems for Treatment of Epilepsy. So just before we start, I want to explain that in plain English. What I'm doing is basically making a brain pacemaker kind of like device more intelligent in the way it treats epileptic seizures. So keeping that in mind, here's a rough outline of my presentation. First, we'll start with the motivation behind the study, what epilepsy is and how it starts. Second, I'll explain some of the methods and studies that currently are being used to treat this. And then we'll get into my study, which has two parts, seizure detection and stimulation to get rid of it. And finally, I'll conclude and finish off with some future works that we're doing. So epilepsy, why do we care about this? Well, because 3 million people in North America and 50 million people worldwide suffer from this to different varying degrees. That's about 1% of the total population in the world. If you've ever seen anyone with seizures, it's a very debilitating condition. So symptoms range from auras to muscle twitches, jerking, as well as sometimes loss of unconsciousness. So if you imagine if you're driving a car or operating any kind of heavy machinery, it's very dangerous for you. Also, it's embarrassing for the patients usually. So what's been done right now to treat it is that people basically take anti-seizure medication, which works to kind of suppress the electrical activity in your brain. However, 30% of the people are unresponsive to this kind of medication, which is about 1 million people in North America. So what they need is basically alternative treatments. So just to explain a bit more of what seizure is. So if imagine, we know that your brain basically communicates to different parts of itself using electrical signals. So different parts of your brain oscillate at different frequencies to communicate with each other. However, when this communication becomes out of whack, the synchronization becomes super strong and your whole brain basically oscillates at one frequency. So nothing can hear each other and you can't talk, and sometimes you basically lose consciousness. What that looks like in an electrical recording of the brain is this. As you can see in the slide, what's marked by the black line is the onset of a seizure, and you'll see that the electrical amplitude increases a lot, and as well as the synchronization between the channels. So what's currently being done to treat these intractable seizures are what's called intracortical implants, and they use electrical corticogram, which basically is electrical recording inside the brain, to monitor your brain activity as well as stimulate your brain as it needs. And there are two main types of this kind of device, open versus closed loop device, and I'll explain what the semi in the bracket means in a second. So open loop devices basically is kind of like a scheduled stimulation to your brain in a periodic fashion. So every hour or so, it will stimulate your brain for 5 minutes. And the hope is that it will disrupt seizures before they form. And closed loop devices work like this. They basically have a monitoring system which records your brain activity and transforms that signal and to take out some kind of useful information out of it. And a controller finally decides whether there is a seizure or not and sends stimulation waveforms to the brain. However, current stimulation methods are not very intelligent in the sense that once we decide there is a seizure, it stimulates the same way for a set period of time until the seizure is gone. So the hope is that we'll be smarter in the way we deal with these kind of things. So there are some more adaptive stimulation studies. I've shown two, and the first one uses a machine learning technique to decide between one of three different stimulation parameters to treat different kinds of seizures at different times. And the second one uses proportional feedback in the sense that we know in control system, it basically injects a negative waveform into your brain to negate some of the effects. And both of these studies have shown positive effects compared to normal controls with just constant parameters. So having explained that, what is the research question of today? Basically, it's to design a closed loop system that is one, accurate in determining the situation at hand, and two, having the ability to flexibly deal with these situations, and three, deal with them in optimal fashion. which result hopefully in an individual and situation-tailored epilepsy treatment. So my project has two phases basically. In phase one, I come up with a model to predict seizures, and in phase two, I'm using a novel stimulation algorithm to try to stop seizures. So yeah, in phase one, I'm using human electrical recordings from the brain, and in phase two, which hasn't happened yet basically, but I'm hoping to use rat models to test this algorithm. So I'll walk you through phase one using an example data set, and this is the picture I've shown before, which basically has 8 channels of recording. I've selected randomly from 64 channels to match the chip that will be implanted in rats. So as you can see, the black line marks where the seizure is happening. And what I'm doing is basically performing short-time Fourier analysis on these waveforms. So the first set of features we have is the log power spectrum. I hope everyone is familiar with this, but if not, basically we're decomposing each signal into its Fourier components, so different sine waves of different frequencies, and we're mapping the power of each frequency across time. So as you can see, as the seizure starts, every channel exhibits an increase in the power for the lower frequencies. The second set of features I have are phase correlations. So if you imagine dividing a signal into components, say between 8 to 20 hertz, and taking just the 10 hertz signal and compare it to all the other channels, what we'll see is that the frequency of these channels sometimes match, in which case the phase difference will be 0, and sometimes when they're completely misaligned, it will be pi degrees. So as you can see marked by the white line, when seizure starts, the higher frequencies are much more aligned, become much more aligned than before. And this effect bleeds out into the lower frequencies. And finally, the last feature is a frequency of max power. And what we observe is that basically when seizure starts to happen, the frequency at which the maximum power occurs becomes higher. So usually your brain exhibits the highest power between, say, 0 to 10 hertz. However, as you can see in this rectangle, when seizure starts occurring, the power begins to increase starting from around 30 hertz. And this plot just shows this one trace what the maximum frequency is, what the frequency of maximum power is at any given time. And you can see marked by the black rectangle, it starts at around 15 hertz and rises sharply to 45 hertz. So I've run through all these features, which basically is a almost 900-dimensional vector, and to use this in a real-time seizure detection algorithm will be computationally intractable. So what I want to see is, can we extract some more useful information out of this? And basically we can. I use principal component analysis to extract the top 3 dimensions, and the result is that those 3 dimensions account for 65% of the total variance. So plotting those three dimensions, because we can visualize these better, we can see there are 2 very distinctive clusters. The blue cluster is the normal, which, as you can see, circles around and goes into the red cluster during seizure. And this lends itself very naturally to a clustering algorithm. So I use the k-means classification, and it's unsupervised. So basically the computer decides for itself when a seizure is and when it's not, without any other kind of information. So this plot shows the result of that classification, and as you can see, during normal times, it's in class 0, and when the seizure is occurring, it hops off to class 1 almost immediately. So this is something that's good. So knowing when a seizure is happening is very useful, but we still want to stop it. So the algorithm I'm using, or I'm exploring, is called the simultaneous perturbation stochastic approximation algorithm. And it's basically a fancy way of saying gradient descent with estimates of the gradient instead of a true calculation. So the main takeaway of this algorithm is that it estimates the cost gradient using 2 measurements only, instead of what you expect, which scales linearly with the number of dimensions that you have. And so that means we can easily implement this for real-time system control. And the cost function that we're minimizing here is the distance of any given point between the normal cluster and the seizure cluster. So if you're closer to the normal cluster, you're basically not having a seizure. And when you're closer to the seizure cluster, we think you are having a seizure. This is a very crude way of putting it right now, but it's a good basis to start with. So as you can see, this is a simulation of the algorithm performed on one of the stimulation parameters, in this case, voltage. So the red trace shows the cost function, and when it's negative, we don't do anything, basically because there's no seizure. And when it crosses the threshold, which is 0, we think there's a seizure happening, and the stimulator starts emitting waveforms to stop that. And the blue lines show the voltage at any given time of what we think should be the optimal stimulation parameter. Keeping in mind here that because this is a simulation, the simulations aren't actually doing anything. So the goal is to test this in a rat to see how it performs, and hopefully it works out well so we can implement it in a clinical system. So in conclusion, what I've developed is so far an algorithm to detect seizure, as well as to treat it optimally and flexibly in every situation. Moving from now, we want to port the system to an FPGA to test it on a rat model, and also experiment with different kinds of stimulation techniques such as spatially sensitive or time varying. So with that, I would like to end my presentation with a thank you to Dr. Roman Genov and Dr. Jose Luis for supervising me and providing me with insights, as well as Tariq and Hossein for helping me through this project. Thank you.